Hello to everybody, my name is Denis, and today we'll have a tutorial on point clouds learning. So I hope after this tutorial everybody will understand how to build neural networks for classification and other problems with point clouds. So as I mentioned, please upload the notebook from the GitHub to the Google Colab and run the first cell with downloading the data. Who succeeded in it? Okay, not so much. As you can guess, point cloud, I will speak while you downloading the data. As you can guess, point clouds is just the set of points. And the main core difference from other types of data, such as images, such as text or audio, that we work here with sets. So, and as we know, sets can be in any order. So set is usually an unordered data structure, and also the networks that we build, they should be they should work with any number of input point clouds, because if you can consider this car, and if we take 1 point out, then we'll obtain the same car, and we should take this into account while designing our neural networks. So the plan for today is to learn how to represent point clouds in data. Then we'll look at how to perform data augmentation, the same as we perform for images while training neural networks. Then we'll build simple classification network. Then we'll make it more complex and build PointNet, which is almost state of the art. It's of course not, but you can obtain pretty nice results with it. And finally, we'll build a point cloud autoencoder, which is a good thing because autoencoder can be used in many generative learning problems, such as in painting, shape completion, super resolution, and I will show you later. If you have any questions, or if you don't understand something, please feel free to ask me questions directly and interrupt me. At the first cell, we can download ModelNet 40 dataset, which is a dataset of point clouds with 40 labeled classes. And all the code for downloading and working with almost all the code is written for you. So please just run the first cell, and who succeeded in it? Okay, you are waiting for downloading, right? Okay, okay. Okay, let me continue speaking, and we'll just then wait. So while you're downloading the data, I could show you some visualization of point clouds. It is better to use Chrome browser or Yandex browser with this notebook in order to obtain all visualizations working fine. So it may not work in Safari. But I'm talking about only about visualization. So if you don't need visualization for some reason, then you could skip my speech. So here is some magic for visualization with the Plotly library. And if you previously worked with PyTorch, you know that PyTorch has very great mechanism with loading and iterating through data, which is called Torch Dataset and Torch Data Loader. And here is written for you dataset for ModelNet 40. So I propose you just to run this cell. Then we could use this dataset along with data loader to just load this in memory and run some functions for visualization that are also written for you. And finally, obtain an airplane. Who didn't succeed in data loading? Yes, you're also waiting, yes, and it's, what is the speed of the loading? 1 megabyte. Okay, I hope it's 1-2 minutes and we'll finish with it. So now, as you can see on the screen, it's a point cloud. We could rotate it and okay, I think maybe I should wait for some time. Are there any questions? Yes? Yes. Yes, the analogy will be the following. It is called shape completion for point clouds. And imagine near you there is a LiDAR scanner that scans what is nearby and obtain a point cloud. And it scans me. When it scans, it doesn't see what is behind me. But if you, as a person, look at me, you know that behind me is a desk, a computer, and other participants of our conference, right? So it is important to complete this absent part that is behind me. You know, understand? Considering discriminative problems of point clouds, there are actually 3 main problems. We are not limited to these 3 problems, of course, but they are like commonly solved. The first problem is classification. So we have a set of points, which is one point cloud, and our goal is to tell what is the meaning, what is the object. So is it table or car or Mac or anything else. Also we have 2 types of segmentation. First is part segmentation and second is semantic segmentation. When we consider part segmentation task, our goal is just to separate one object into a number of objects. And not to tell their class, but just to separate and tell that they are different. And considering semantic classification, our goal is to label points. So to say that this point is chair, this point is table, this point is sofa, and so on. And the PointNet, which we will consider today, solves all this problem. However, we will be limited due to the time limits only to classification. If we talk about point cloud representation in memory, it is very, very important to note that our representation doesn't actually correspond to our real nature of points. So as you can see on the picture, we can mix points. So we can mix the order of points, and all these points will be stored as a matrix in our memory. And if we swap 2 points, then we will obtain the same point cloud. It will be almost, not almost, it will be completely the same. But if we swap 2 elements in the matrix, it will be a different matrix. Also, as I mentioned at the beginning of our seminar, if we take away 1 point from the point cloud, it will be the same point cloud. So if we will consider a car and take out 1 point, it will be the same car. And all algorithms that we build have to take this into account. In other words, or more formally, we should consider such functions, because neural network, as you know, is a function, and we should consider such functions that are permutation invariant. So if we change the order of our points, then we'll obtain exactly the same result. Simple examples of these functions are maximum or sum function. Another example may be an average. And actually, many algorithms of point clouds learning are based on maximum and sum functions. So are there any questions at this moment? And who is struggling with data? Okay. But are there any questions considering what I told? Yes? Sorry, could you please? Movie objects? Moving. What other the same algorithms for tracking moving objects? It depends on the nature of the data. So if it is moving point cloud, for example, when we consider self-driving cars, for example, yes, like Yandex, which is going somewhere here, it uses LiDAR scanner, and it obtains point clouds. So, and every second it obtains a lot of points, you know, that is surround the car, and everything is moving. So yes, these algorithms somehow work with moving data, but it depends on nature, of course. Okay, who don't know what is data augmentation? Okay, good. Everybody knows. So as you know, for data augmentation, for example, for images, we use such methods as rotation, as translation, as random noise, as decolorizing, and anything that is inside your imagination. For point clouds, there are actually 2 based augmentation methods. First is random jittering. It means that we take each point and randomly move it. So we add a noise to it. In fact, we randomly move it at any direction, or just along any direction. And the second is random rotation, because we know that if we rotate point cloud, we would obtain the same point cloud. And your task for the current moment will be just to run random jitter, because it is implemented. You can see here that some points are on different places than on the original one. So on the left, it is an original point cloud. On the right, it is randomly jittered point cloud. All the transformations I implement using PyTorch transformations from Torch Vision package. And now I would ask you to implement random rotation. It's just, it's really easy, I think, because data is our array, which is our point cloud. So it is a matrix of size n to 3, where n means the number of points and 3 means x, y, z. And our goal is just to do a rotation of each point. If you don't remember how to make rotations, you can just open the link from Wikipedia and remember yourself rotation matrix. Yes. Really? Could you show please? Нет, я думаю, zip можно закомментить, RM убрать. Да, и вот после такого. Вообще она скачалась. Ну вот, папка есть. Вот она. Можешь просто открыть? Да. Вот, слушай, ну давай попробуем дальше. Это очень странно, потому что все работало. Посмотришь? Are there anybody who struggling with unzipping the data or who have some failings in data loading? Still don't load. Okay. What should be next? Any. So you can select. Why do we need what? To rotate. Because we select random angle and then we rotate on this angle along any direction. Does it make sense? In order to implement the rotation, you just should multiply each of your point to the rotation matrix, which is different depending on the axis that you want to rotate on. Who has any problems? Okay, who succeeded in implementing rotations for point cloud? Okay, and other are just doing, right? I published the solution on the screen for for rotation. So, and everything we need to do is to compute np.cos, np.sin, and create a rotation matrix based on these computed values, and just multiply our data, which I think reshape is maybe not necessary here, to multiply our data on rotation matrix using np.dot. And if everything works fine on the next cell, in the next cell, you will see on the left original point cloud, and on the right rotated point cloud on some random angel. Sorry? As you wish. So it's as you wish, really. You can select any axis or multiple axes, or in fact it doesn't matter. For the current moment, the goal is just to understand the augmentation and understand why it is very good on point clouds, and that it is very useful because we can multiply the number of samples in our data set many times. After rotation, you could see the results. There is a plane and a rotated plane on some random angel. Other important transformation that we usually have to do is scaling. So as you know from machine learning that there are basically two types of commonly used scalings. First is normalization and second is scaling. In one case, you make our data lie in cube from 0 to 1, and the second type of scaling is when we make our data have mean value 0 and standard deviation 1. So in my case, I implemented scaling to the box, to the cube of size, to the cube from 0 to 1. And usually we hope that this transformation will help us in learning of any task, both classification and autoencoder, and in fact any task. After we implemented each transformation, we could compose them together and load our data set and use PyTorch data loader for iterating through our data. As you can see, there is not so much difference from images or other kinds of data. There are pretty different rotations, jittering, and there will be a huge difference in network's structure. So our batch size is 64, then we'll have 154 train batches and 39 batches. Who have some questions for the current moment? Who don't understand anything? Is it easy, or you're just downloading the data? Okay, so now our goal will be to build a simple point cloud classification network. And the recipe is actually the same as for images, for example. We need some optimization algorithm like like stochastic gradient descent, and I will use Adam as the most sophisticated and most as the best actually algorithm for many tasks. We will use cross entropy loss function for optimization, because our problem is 40 classes classification, and we could, for simplicity, we could use accuracy as our measure of quality in order to understand how well is our network performs. And I have written two functions. First is evalNet and second is trainNet. They both do all the training work for you. So trainNet is a function which iterates through your data and perform weight updates, and evalNet evaluates your network on test set and measure its quality, visualize some samples, and so on. Maybe not visualize. So who is not with me at the current moment? Everybody with is fine with data loading, right? Good. So, what will be our point cloud network? As I said, our goal is to build a function, neural network is a function, that is permutation invariant. And for this goal, we can use maximum or sum function. Let's use, for example, maximum. Why not? Our input shape that we will work with is batch size to endpoints to 3. No, I think it's clear. Then our second layer, our first layer, will translate each point from 3-dimensional space to 64-dimensional space. 64 is just a number that I propose to use. It's not, of course, obligatory. This should be a linear layer that transforms from 3-dimensional space to 64-dimensional space. But the important note that it should work with each point separately. So it should be applied to each point separately. On the third step, so it will be our second layer, we will use maximum, and we will get rid of endpoints dimension. So we'll obtain batch size, we'll obtain shape batch size to 64. And after that, we could transform our batch size 64 to the shape batch size num classes. So this is actually what we want for classification. Let me dive deeper into details about our first layer. So as I said, our goal is to transform each point from the 3-dimensional space to 64-dimensional space. We can do it in two ways. The first way is to use linear layer. This is okay, but this will be not convenient. And I can't explain why this can be not convenient, but just believe me, just believe me for the current moment. A bit later, I will show you why it is not convenient. The alternative, which usually people use, is to use not linear but conv1d layer with the kernel size 1. It gives totally the same results as linear layer if we use conv1d layer with a kernel size 1. It's a bit slower, but much convenient in implementation of neural networks. So let me code with you, and we'll see what is happening here. So by the way, here I've written some text about the difference of conv1d and linear layer and how we should implement everything. So if you are interested, you could read now or later. Okay, we should define our layer. Let's call it self.first layer, and as I said, let's use conv1d layer. What it should actually do, it should transform from 3-dimensional to 64-dimensional space. Then here we say in channels 3, out channels 64, and kernel size 1. After that, after this layer, we will use maximum function, and let's do it. Okay. So we have x, and x have shape batch size to n points to 3. We apply first layer and say that x is equal to self dot first layer of x. Then we should apply sorry, here before we apply first layer we should do transpose operation on our matrix, because it's just because of the documentation our conv1d layer works with the shape I will write here. So conv1d works with shape batch size 3 endpoints. So that's why we should just write x is equal to x dot transpose 1 and 2. It means that we just swap first and second dimension. Who don't understand it? Okay. Then we apply first layer, which is conv1d, and here we have shape. Which shape should be here? Who can tell me? Batch size is 64 and endpoints. Okay, thank you. So here we have shape batch size 64 endpoints. After that, we should somehow get rid of endpoints dimension, as I said. This will make our network permutation invariant and will allow us not to depend on the number of points. That is why we just write here x is equal to torch.max of x2, and please take a note that here we should mention the dimension along which we along which we take the maximum, and this is the second dimension, so dimension endpoints. And the second important note, I write here x, but I'm not wrong, because I should write something like this, because torch.max returns two values. Just be patient, be careful with it. It's a maximum and it's arg maximum, so just we are interested only in maximum. Now x has shape, batch size, and 64. So in fact, what we actually did, we transformed each of the point clouds in our batch to one vector. So we created a single vector representation of each point clouds, which doesn't depend on the number of points in the point cloud and on their order. Who don't understand it? Or who has any other problems? Okay. It's exactly max pooling, but the idea is that we get rid of points dimension. So we don't depend on the number of points, and we don't depend on their order. And we could obtain one single vector for point cloud. So as an input, we have a set of points in three-dimensional space, but now we have only one vector for the whole set. And which is good, we could use it for anything you want and anything you know from deep learning course. For example, you could transform each 64-dimensional vector to 40-dimensional vector and solve our classification problem. So for this reason, we need a linear layer, self.linear, which is equal to nn linear from 64 to, I wrote here num classes. And we can apply like x is equal to self.linear of x. And who remembers what should we do after the linear layer, after last linear layer when we do classification? Yes, thank you. So who don't remember, if any, we should transform our x to the vector of so-called probabilities. So our network is ready. I propose to run it and test if everything works fine. So here we just run trainNet function, and I hope we will not get an error. Yes, it absolutely doesn't look at the relationships between points. This is just the beginning of our, you know. Sorry? No. It will not work. It's just one layer network. So yes, of course, it will not work. Yes. Here is the calls, and we can show you layers also. Here? Okay, yes, you should understand that this is one layer or two layers linear network, and it will work, of course, very bad. But this is an important concept when you transform a set of something to one vector. And you could do after it, you could do with this vector whatever you want. No. Exactly this network works with any amount of points. If we consider practical part, of course, if we, if there will be too many points, it's okay. If there will be 2 points, then it's of course not very well for any task. It's like an image with 2 pixels. Okay, so something is happening, and I propose to stop this. It's stopped. Okay. So now we will consider PointNet. PointNet is like an extension of the network that I showed you just now, and it consists of several parts. There is a which you can look on, but propose you to just briefly discuss it and start implementing it, and then we'll understand everything. So what is actually PointNet? It is a network that consists of linear layers that also applies, as we did before, for each point separately, and transforms from 3-dimensional space to 64-dimensional space, then from 64 to 124-dimensional space. So it's just transformation of each point. After that, we again take maximum, and then we use some linear layers, softmax, and obtain classification. But there is a very good thing which is called input transform, which is here on the image, and what it is about. Usually it is very good if we can make our network that we could help it to work with rotations of point cloud. So we want our network to be rotation invariant. But if you can understand, our previous network is not rotation invariant at all, because if we do rotation, the coordinates will change, and the result may change. So our network may change completely different class for the same object. And the authors of PointNet proposed how to overcome such limitation and how to make it rotation and any other linear transformation invariance. What we actually do, and what is their idea, they say, okay, rotation, in order to perform rotation, we need 3 to 3 matrix. We need rotation matrix with sinus and cosinus. And when we have rotation matrix, we just multiply this matrix to each of our point and obtain rotation. Everything is fine. And they say, okay, why not to predict this rotation transformation? So we have some point cloud as an input, and why not to predict how we should transform this point cloud to some like canonical way? It's like I call it canonical way, but the idea is that they transform point cloud by multiplying on something that depends on this point cloud. Here you can see. we have some X, which is our point cloud. And we have a T-net. T-net is some transformation that takes our X as an input and return a matrix 3 to 3. We can call it transformation matrix. And then we just multiply our X and this transformation matrix, which is an output of our T-net. And the important that T-net is also depends on X, depends on input point cloud. And we can consider, it of course can be not, but we can consider T-net as a prediction of rotation or of translation matrix, which we after that multiply by X. Who don't understand anything? It doesn't need to be yes. 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 But what is the rotation? Angle? Angel? Yes, I understand. I think we could, so why not? But yes, and in fact it's good because if our network is works fine with any transformation like rotation, like you said scaling, right? Like translation, maybe when we mirroring the point cloud, it's in fact good because it becomes more like, I don't know, like smart. It's a bad word. It's a cup. It's a cup, rotated cup. You see, I see. This is a cup, and I, as you know, me as a human understand that this is a cup. This is a cup, and if you just scale it like this, I will also understand that this is a cup. And no, I partially agree with you, partially I disagree, but this is philosophical question. Okay, I think we can predict angle, right? We can predict only rotation, or we can do like any transformation. So it just I think authors of this paper, they had some goal. For example, obtain good classification results, right? And they could try this. Of course, all these things are like your finger to the sky, just like, let's try this, right? Then try this, then try this. And it seems that this works better. That's all. Okay, are there any questions about transformation net? Why do we need it? Yes?
So what if, so you have two cups?
Yes.
What if the one cup has, I don't know, 3,000 points and the other cup has only 1,000?
Yes.
How can you ensure that the rotation angle, rotation matrix will be the same?
This rotation matrix depends on the input point cloud. And you ask, yes, that if we have different number of points, then we will obtain different transformations, right? I can answer you like, so what? I mean, it can be different and
Then if the output, sorry, if the rotation matrix is different,
yes.
then your cup will, for example, be like this, and the other cup will be like this.
You know, we are now mixing two types of thinking. First type of thinking is that we have a data set and we want as high as possible accuracy, for example, right? And second thinking is just we want to build AI that is like human, right? And we are arguing with you and with colleague about caps and transformations. It's all about how we can build AI that is like human, that thinks like human. But if we think in a way that we want to solve this classification problem, exactly this, and increase score, then it may differ. Understand what I think? Or
maybe I understand
no, I say that you are right, but it doesn't matter. Like this. So if we obtain better results, so why not? Maybe yes. Maybe we'll obtain better results if we take what you are saying, number of points into account. But here we don't take. So whatever we want. Yes.
So the process has some dysfunctional application number of points of measures. Do they use this separation?
Do they use this separation for?
Elimination of dimension corresponding to the number of points.
In fact, no. I haven't seen any algorithm, any layer for point clouds that are somehow limited on the number of points. No, it is limited in like memory of GPU or CPU, but not in your PyTorch code. Yeah. I think they work with objects with any kind of, I mean, much, if you look at this image, I think this is much more complicated than a donut, right? On the right, semantic segmentation. So, in fact, we built PointNet is the same part that is used for semantic segmentation. So, yes, answering questions, yes, yes. Yes. We shouldn't. So I just told you about rotation as an example that we could learn rotation, but it can be translation or any other magical transformation. Any other questions? Okay. So I wrote TNet for you. We could just run it, and it's interesting to look at its structure on of the first layers. So here we have again conf1d layers from 3 to 64, from 64 to 128, and from 128 to 1024. We apply layer by layer, then we apply Bayesian normalization after each layer, and then we apply ReLU nonlinearity. And we do this 3 times, and after that we again use maximum function. Then we again obtain for each point cloud, we obtain one vector, which now our goal is to transform this one vector to a matrix of size 3 to 3. Okay, I propose you to together implement PointNet. So what have we here? We obtain some x, which again has shape batch size to endpoints to 3. Then we predict the transformation that I told you about, and we multiply torch BMM is batch matrix multiplication. We multiply this x to our transformation. Okay. Now what will be our shape? Who could tell me? No. Sorry? After batch matrix multiplication, what will be the shape? Batch 3 endpoints. Endpoints 3, I think, yes. Because, yes, initially it is batch endpoints 3 and it stays the same, in fact. So, here it is batch endpoints 3, and after multiplication it is the same. Okay, now we could in fact copy some parts of code from here, and let's look how can we apply it. So conf1d. No, let's write self.main is equal to anon.sequential, and here we'll write all our layers. So first layer will transform from 3 to 64 each point. Then we will obtain batch norm with dimension 64. Note that batch norm 1D is not 2D as for images. Then we'll obtain a non.relu, and as I remember, we should write here in place equal to true in order to make the transformation in place. After that, we could repeat it. As far as I remember, I can miss something, but it is necessary by like PyTorch syntax if we use it inside sequential. But I may be wrong. Okay, so here we have 64. Then we translate from 64 to say 128. Batch norm 128, and from 128 to let's say 124, and here we have batch norm 124, and I propose not to use here relu, but to use maximum layer after it. So we could apply self.main and say x is equal to self.main x. Here we'll have shape batch size, then by the way, as you remember, I asked you to transpose all your x, so we should write here x is equal to x dot transpose 1, 2, and here it will be the shape batch size, then 3, then endpoints. After it we obtain, we apply main function and obtain shape batch size to 124 to endpoints. So for the current moment, each of our points is represented as a vector of in 1024 space. And it's time to apply maximum function. Along the dimension 2. So in order to get rid of endpoints. And after this maximum, we will obtain one vector for each point cloud. So are there any questions for the current moment? What is the idea behind this maximum? We would like to build a network that is permutation invariant, so it doesn't depend on permutation of points inside this matrix. Second, we want to make our network invariant to the number of points. Because you will have, for example, 2000 points and 2001 points, it will be the same point cloud, but in memory it will be different objects, different matrices. With one vector. It is 1024 dimensional vector. And it depends, in fact, from many points. Okay, now we have 124 elements for each point cloud, and what we can do here, we can just apply, let's say, one linear layer. Let's get rid of it and create an n.linear from 1024 to again num classes, and this will be self.linear and self.softmax is equal to nn.softmax on one dimension. So x is equal to self.linear from x, and x is equal to self.softmax from x, and that's all. I made a mistake. Softmax should be from like here. Yes, and again, in the next two cells, they're just the network definition and calling the training of this network. So now I think we don't have enough time for training this classification network. It may run while we are talking. And are there any questions about classification network? So this will be pretty nice results. So if we tune it a little bit at, yes. I could see the relation of this maximum operation to max pooling, for example, but I haven't seen that somebody applied like maximum along pixels dimension something. It's very strange, and in fact we don't need it for images. So here we do it because we can't do anything else. Almost can't. we can do something, but it's pretty useful technique. Yes. I can't say that it is projection. You know, about correspondences between points, do you know what is attention mechanism? Maybe you heard about it. Like all state-of-the-art networks for NLP tasks are made of transformer architecture that is called, and attention mechanism. Maybe you heard BERT or GPT-2, and in fact these transformer models can be easily applied and out of the box applied to point clouds. And what attention actually do, it again doesn't depend on the number of points, and it helps to learn the correspondences between points. And there are some scientific papers on archive, on conferences such as CVPR that considers application of attention layers to point clouds. So it's just like 1 year later in research of point clouds. If you use attention, if you use it depends. I can't answer. Okay, are there any questions about classification, or we can move forward to Autoencoder? Yes. Yes. No, yes, I mean, I'm listening. I would not consider such type of architecture for images because for images we have convolutions. Convolutions are really good, and this is like almost all we could do with point clouds, because point clouds are very like bad and inconvenient type of data. Images are much more convenient because we have regular grids. So why do we need this stuff if we have convolutions? They're just much better. Okay, any more questions? Okay. So as you can see, our accuracy is increasing, and as you know, if we tune a little bit, if we play with parameters, with learning rate, and so on, we'll obtain much better results. Now I propose you to switch to generative learning. And generative learning is also an important task in practice, and as I said, it is important even for self-driving cars, which are becoming more and more popular. And I will tell you about 2 generative learning tasks, and all of them are based on Autoencoder. So first task is shape completion. On the left you can see a car which usually you obtain when you consider LiDAR scanner data. So it's very like rare, so points are rare, and you can see that yes, actually this is a car, but this is really incomplete. And in order to run some algorithms of classification, segmentation, or something else, it would be good if we could complete it and make the complete car, and after it we can improve and use other algorithms such as classification. The second type of problem that also take place is upsampling. So it's a similar problem to image super resolution. So when we have low resolution image and want to obtain high resolution image, we can do the same with point clouds. When we have, for example, 1,000 points and we want to make 5,000 points for some reason. For example, we want to see more details or want to run other algorithm more efficiently. So that's why we need it. And usually for these problems, people use methods that are based on autoencoder. I hope everybody knows what is autoencoder considering images. So if not, please raise your hand and I can explain something. Okay. The goal here is the same. We have input point cloud, which is here again a matrix of size and points to 3, and we would like to have an output point cloud which is the same, which has the same size, and at the middle it is a bottleneck of this autoencoder, which is a good vector representation of the input point cloud. If you would like to apply such an architecture for example, shape completion, you just replace your left point cloud with incomplete and learn how to take this incomplete point cloud as an input and obtain complete point cloud. In order to construct autoencoder, it is important to measure distance between two point sets. For example, when we learn autoencoder for images, we consider L2 distance between pixels or adversarial loss or any, but we have well-known distances between images. Considering point sets, there are actually two commonly used measures of distance between them. First is chamfer distance and second is Earth movers distance. Here is a formula. You can look at it. It is pretty easy, or you can listen to me. So the idea, intuitive idea behind this chamfer distance, which we consider today, is the following. We have two sets, and on the left part of this formula, for each point of our left set, we consider each point of from the right set and find the minimum distance. So for each point from the left set, find minimum distance from the right set and sum up all these distances. And then we do the following. We do the same swapping the sets. So we for each point of the right set, we find the nearest point on the left set, compute its distance, and sum up everything. This is a nice differentiable way of computing distances between two sets. Are there any questions about it? Yes. Euclidean distance, yes, because we're in three-dimensional space. Are there any questions? Okay, see everybody's tight and we are almost done. So chamfer distance, and now our goal is to implement encoder and decoder. In order to implement encoder, I propose you to take the code from PointNet. So I hope you understood when we transformed our point set to some vector representation using PointNet. And this is, in fact, can be our encoder. Let's do it. So I just copied the part from PointNet, which is 3 convolutional layers, conv1d layers with batch norm with ReLU between them. And then, before it we should transpose, as I said, x is equal to x dot transpose 1 and 2. And in fact, this is our encoder. So the max function is already written, and here you can see max indexes. I will tell you a bit later. And now our goal is to build a decoder. In fact, there is not too much science behind decoder implementation, because as an input we have, for each point cloud, we have a 1024 dimensional vector, and we need to transform it to the matrix of size and points to 3. So what we just do here is just we say that we have some main block which is an n dot sequential, and here we can do the following. An n dot linear from 1024, which is our bottleneck size, to, for example, 248, then an n dot batch norm 1d 2048, then an n ReLU, then again an n dot linear from 2048 to 3.2048. Look at what is happening here. We just transform one vector to a very big vector of size 3 multiplied by 248, and after that we will just reshape this big vector into a matrix of size and points to 3. So we say x is equal to self dot main from x, and x is equal to x dot view minus 1, which is batch size, 248 and 3. And last thing that I want to say about decoder, that at the end of it we could add sigmoid layer, because we know that all of our points, because of scaling that we wrote before, all our points lie in cube from 0 to 1. Then we can just write self dot sigmoid, and it will make our learning a bit easier. So, and again, are there any questions here about decoder? Or, yeah. You know, GANs and like standard generative models with noise and so on are rather hard for point clouds. So there are some works, they are very hard, and I just want to show you how we can do something small and easy to do and obtain results. No, we can, yes. There are different types of models, yes. It's just because we are limited in 1 hour and a half, I just show you simple and practical useful cases. Are there any questions? Okay, I see everybody is tired, and now we could just run Autoencoder, and after maybe 10 epochs of training, you could see. So at the first row you could see original point clouds, on the second row you could see predicted point clouds on 3 different views, so with random rotations. So after 10 epochs it will be a bit similar, but not the same. After maybe more epochs or more tuning, you can obtain point clouds that are very close to each other. The last thing that I wanted to talk to you is so-called critical set. So here is a cell which I propose you to run after training of Autoencoder. However, I inserted visualization from original PointNet article, and this maybe will give you and understand the idea behind why we took this maximum. So we have some original shape which is on the first row: a table, a gun, a lamp, and so on. There are 2048 points in each point cloud. However, when we take maximum operation, what we actually do, we have each point lie in the space of size 1024, and we take maximum along the endpoints dimension. So if we have a matrix of points, and we consider columns as an axis where we take our maximum, and we get rid of endpoints dimension. In fact, we consider first coordinate and take maximum value among all points, second coordinate and take again maximum values along all points, and so on. And we can think that not all points will play their role in the final vector. I mean that we take on each column we take maximum, and there are some points who doesn't play a role at any maximum, at any element, any dimension. Who don't understand it? Okay, who understand it? Okay, good. So some points play a role, some points not. And if we visualize points who play their role, who are important, we could see the following picture. So the second row, you could see that all these points, which the authors calls critical point set, they, for us, for humans, they represent the object very nice. So you see at the first picture and you see the table, you look at the second and you see a gun, and actually what we do, we find like key points. So points that are important on our point cloud. And because other points, they don't play their role in the maximum, we can just get rid of them. And it occurs that from 2048 of input points, we can leave only, for example, 400, and we don't need other points. And so we could reduce all the amount of memory we spend to 4 times. So on the third row, they visualized all the points that we don't need at all, that our algorithm don't need at all. Okay, if we look at the results of Autoencoder, you could see here is the table, and here is something like we call drunk table, maybe. If we learn more, and if we can try use another measure of quality, not chamfer distance, we could of course increase the results. So for me it is all. thank you. If you have questions, please ask now or later. How they are estimated? When we calculate maximum, we consider first coordinate. We have 1000, for example, coordinates. We consider first coordinate and then take maximum. Maximum, and there is a point where we consider, where we found this maximum. Understand? No? Here is our matrix, right? Let's consider the first one. We take maximum on the first column. For example, this is x1. Then we say the first point is important. Then we consider second column, and the maximum is y3. Then the third point is important. Then we consider this column, and z4 is maximum. Then we say that fourth point is important. And this is our three critical points. And in fact, we don't need point 2 and 5 at all. Understand? So the same as when we have 1000 dimension. Any other questions?